So let's move on then to talk about semi-gray surfaces. And this will be, I think, the last topic. This is the last topic of the class. So we've made it this far. Semi-gray surfaces. So a semi-gray surface is kind of as implied here, is a surface that in certain regions is gray. If you take a low wavelength and a high wavelength, in that region, we're going to assume that the surface has a constant emissivity. But we're going to discretize that surface enough times that we can actually capture longer term or longer span changes in emissivity. So for this example, what we're showing is we have some plot of emissivity, and we've discretized this into, in this case, 3, or actually NB. And so NB bins or categories or bands, I guess, whatever you want to call them bands. So there's N bands that we are discretizing into. And then for each of these, we just assume that it's a gray surface. So what we're going to do is come up with models that help us relate the radiation exchange in each band. Right? So I think a couple things here, just kind of bookkeeping things. There's subscripts that we're going to need to worry about. When we're writing out our radiation problems, we've been talking about surface I, surface J. We now need to introduce an additional subscript. Okay, so just to keep track, our first subscript is going to be I or J, right? That is the surface index. The second subscript is going to be W. Okay, and this is going to be the wavelength band. All right, so you're going to have a surface I that has NB different bands. So there's N surfaces, NB bands. So you might say my heat transfer from Q dot I, right, surface I, in band W is a certain amount, right? And now we discretize based on both of those things. Okay, so let's see. Let's write out the equations for these. Here's our little plot again. So let's write out the equations for these, and then I'll go through some of the nomenclature in the equations. All right. So first of all, we need 2 times n equations. Okay, so the first would be a surface resistance. This is going to be Q dot I comma W is epsilon I W AI EB I W minus J I W over 1 minus epsilon I W. Okay, so this is 4i in 1 to n, and W in 1 to NB. Okay, the second set of equations, and then, like I said, we'll talk about nomenclature. QIW is equal to AI times the sum for J equals 1 to N, right, the number of surfaces, Fij JIW minus JW. This is, again, for I is 1 to N, and for W is 1 to NB. Okay, so let's talk through the nomenclature. I think some of this is obvious, but it's maybe not clear why we're choosing the indices that we are. First thing would be A. Let's do the easy one first. So area, AI. This is the area of the surface I. As we discretize our surface into these different bands, the area associated with each band doesn't change, right? It's just the area of the surface. We're always considering surface area AI. Let's see, epsilon IW, that's the other one that's maybe a little bit obvious. So we have now epsilon for surface I, the emissivity for surface I in a certain band W. That just corresponds to that plot over there. So in fact, what you could have is for each surface I, you might have a different plot, right? Each surface might have different emissivity characteristics. And you might have different bands for each surface. Right? You might say, I'm going to discretize my surface 1 into 2 bands, and I'm going to discretize surface 2 into 10 bands or whatever, just to capture the necessary detail that you need for each surface. In the end, though, you have to agree on a certain number of NB bands that apply to all surfaces. So if I said 2 bands for surface 1 and 10 bands for surface 2, those bands have to exactly line up at some point, right? So we'll see how that kind of works out in an example problem, but just be aware that NB is going to apply to every single surface equally. Okay, so let's actually write out the other ones that maybe aren't so obvious. So we have Q dot I W. So this is the net radiation for surface I in band W. Right? Surface I in band W. So think about this a little bit. I mean, it's not that difficult, but I could have Q dot going from surface I to surface J that's positive in a certain band. And in a different band, I could have the reverse happen. Right, so this now opens up a degree of freedom where you can start having like net radiation exchange that's very different based on the band that you're in. Okay. So Q dot IW, let's see what else. Q dot. Oh, so then if I want to get to Q dot I, how do I get the total heat transfer for a surface I? Well, that's just going to be the sum. Right? It's going to be the sum of all bands. So I would say that's equal to the sum for W equals 1 to NB of Q dot I W. Right? So that's going to apply for every single surface. Let's see. Next one would be the black body emissive power for IW. This is black body emissive power for surface I in band W. Again, same thing as Q dot. You can have different black body emissive powers depending on the band, like for sure you will. So that's pretty obvious. There's a few things we can get out of this. So black body emissive power in a particular band would actually be evaluated as lambda low for band W to lambda high for band W of Planck's law, right? E B lambda I. E lambda, right? So I can integrate the black body emissive curve from lambda low to lambda high and get my black body emissive power in that region, right? Maybe obvious, but this is actually equivalent to the external fractional function times sigma t to the fourth in this region, right? So we would say, what in E's it would be black body. So black body for T I, surface temperature, surface I, from lambda low W to lambda high W times sigma Ti to the fourth. Right, so I can get EB IW using external fractional function in that band times the total black body emissive power for surface I. Okay, let's see what's left. We haven't talked about J. So J IW is the radiosity. Radiosity of surface I in band W. Okay, so that gives us all the information we need actually to solve these problems. So the general methodology is really not different from what we've already talked about. It's just now instead of having n surfaces with n energy balances and we're exchanging radiation on the entire surface, or the entire wavelength, now we're discretizing, doing the same energy balance n times nb times. Right? So we're making it a more complicated problem, but from a programming perspective, all you're doing is adding another duplicate, right? It's really not that much more difficult. So this is how you handle the radiation exchange, and then we'll actually see how the surfaces, depending on their band, the heat transfer works in those surfaces depending on the band.